everyone. I'm going to go over some core principles of confidence intervals, as well as use code to find them in R. So we're going to talk about bootstrapping and using the infer package. So I suggest opening my link that I've put on the same post where you found this tutorial, because it is my personal notes from when I took Stat 20 and guides you through everything we're going to talk about today. My notes are going to have some extra things that I'm not covering in this video, and they're just some extra information. I really want to focus on stuff that you will need for the lab. If you're looking through the note sheet later on and you see something that you're not familiar with or you don't know, don't worry about it, because content differs from semester to semester in Stat 20. So some things that I've learned are not things that you would need to know. So I want to start by defining some terms. So parameters are numerical characteristics of a population or phenomenon. These are fixed values and do not change. Statistics, however, are estimates of these parameters. They're estimated from a sample. So if we look at this example of partisan antipathy, ignore, our population would be all registered Republicans and Democrats. And the population parameter is the proportion of Republicans in 2019 who see Democrats as close-minded. Because we're interested in a proportion, the point estimate is the sample proportion. So in other words, our statistic is a sample proportion. It's a specific value that we get from our sample. We can hypothesize that this population proportion is 50% if we made a guess that half of the Republicans feel that Democrats are close-minded. Now, the thing here is where confidence interval comes in. We do not know exactly what the true proportion is. The statistic we yield from sampling is just an estimate. Confidence intervals allow us to generate an interval where the true proportion parameter could be, with some specified probability of success of actually capturing the population parameter, or in our case, the proportion inside this interval. So the probability of success is called the confidence level, and it's the 80, 90, 95% we talk about in class. Because we aren't sure what the true estimate is, we can only say that we are blank percent confident that the parameter that we're looking for this population is between this number and this number. For example, about this partisan antipathy, this could look like we are 7% confident that the proportion of Republicans who think Democrats are close-minded is between 63.9 and 64.1%. This means that we've generated a confidence interval with a 7% probability of success of actually capturing the true population proportion within it. So now with confidence intervals, there are high and low confidence. High confidence intervals will have very wide intervals, and low confidence intervals will have very narrow intervals. Why? Well, if you have a bunch of numbers in a range, there's a higher chance that the correct value is somewhere in there. Imagine having a bunch of pencils and pens, and you're trying to find a blue pencil. It would be easier to say that I'm 100% confident that there's a blue pencil somewhere in here. But if you remove a subset of the range, some of the pencils and pens, your confidence goes down. Your blue pencil could still be in the sample that you're working with, but you could have also removed it. By narrowing the range of pencils and pens, you have a higher chance of finding the blue pencil if it was still in the sample. So, for that reason, low confidence intervals are more precise, but the trade-off for a smaller interval is less confidence. Because if it contains the true population parameter, we've reduced the probability of success. Now that we've covered some basics about the confidence intervals, let's move on to Bootstrap. So we're going to scroll down here. The Bootstrap is a method where we continuously sample from an existing data frame with replacement. This generates samples from our original data, which is essentially making data from existing data, and simulates resampling from the population. Now, this requires that n, the number of observations, is large. It's because if n is large enough, it would look similar to the true population distribution. Recall that the empirical distribution converges to the population distribution. If n is small, then there's potentially not enough samples to approximate the population distribution well enough. from the sampling distribution. So we're going to move to RStudio in the notes here. And we want to talk about putting these concepts together. When it comes to making confidence intervals, we want to make a large enough sampling distribution using the bootstrap in order to have better confidence that our statistic is in a certain range. So as always, if we scroll to this part right here, this intro breakdown of infer coding puts all the code that you would be seeing in RStudio with the output that it has. So as always, you're going to start with the data frame you're working with. In this case, it was Pew. I don't remember what the question was about this, but we can just assume it's very similar to the Republican versus Democrat example we were talking about earlier. So for Pew, we are going to specify the response and the success. So the response is a variable you want R to look at and draw from, and success is what you'll be using in the calculations. In this example, we'll say that the response in this variable is called closed, and the success is an observation called yes. So to make the new function generate, we'll be making two new data sets from the observation of the first data set. We'll need to specify this type as bootstrap, just so that R knows that it'll be sampling from Pew's closed variable column with the replacement. Looking at the screenshot next to this code, we can see that the replicates consist of yeses and nos. This is fine because we determined success to be yes, and this generate function is solely being used to create more data. The success part of the code will come later. Now we need to find a point estimate or an observed statistic. The example here in my notes is finding the mean of penguins that are Adelie, but in the example that we were working with, a statistic would be the proportion of yeses in the closed variable. So instead of mean, we would choose something like finding the proportion. So this is where stats come in, this is where success comes in. Using calculate stat equals prop, we're going to find and print the proportion of observations where the response variable closed value is yes for each bootstrap data set. And make sure that prop or mean or whatever you're calculating is in quotations, otherwise it could break. So we're calling that proportion statistic or stat. And we can see here that we've created two bootstrapped data sets and we're finding the proportion of yeses in those response variable columns. Okay. Now, to use all this funky data we got, let's make a confidence interval. I've saved the above, so we're going to scroll all the way down here. I've saved the above bit of code into boot, and that is just so that I can talk about it later when we get the confidence interval. Now, an important thing to note is use set.seed parentheses at the beginning of your code chunk, similar to this. And we're going to type a random number in there. Doesn't have to be anything. And this saves your bootstrap data into like a little memory chip in R for you to use later. Otherwise, because generate is doing randomized sampling, we'll keep making new data sets every time you run the code. This could shift your intervals slightly because the data will not be consistent from code run to code run. So set seed basically just saves what you have and doesn't let it, redo itself if you call upon boot later. So in this, we pipe boot into the function get_ci, and we set the level. In this case, we want to use a 95% confidence interval, so we'll use 0.95. This now finds the upper and lower bound of the 95% confidence interval of all the bootstrap data's proportions, or the statistic. In other words, based on the output, we can say that we are 95% confident that the true proportion lies between this 0.628 and 0.653. So if you want to see what this looks like, I have made a little visualization here for you, and we can see what this interval means. We are 95% confident that the true proportion of Republicans who think Dems are close-minded is somewhere in this blue region, if we were talking about our previous example. If you increase the number of replications, the distribution becomes smoother because the sampling distribution is being approximated better and better. The larger amount of data means that the bootstrap will match the sampling distribution of the statistic, and the estimate will be closer to what's true. If you decrease the number of replications, for instance, the width of confidence interval will increase. So down here. And you can see that the x-axis has very wide intervals, and that's because we've decreased the precision of our 95% confidence. So as a side note, I want to make a distinction between making confidence intervals through Bootstrap and the normal curve. Using the Bootstrap is whatever we did up here a few minutes ago, using getCI and bootstrapping the data. But the normal curve is kind of like a probability game. So if we're going to pull up a normal curve right now in stats, we can see that we want 95% confidence. This is a better picture, actually. So we want 95% confidence, and that is all the stuff under the curve here for between this line and this line at the red. So we want to be in the part of the normal curve where the area under the line is 0.95 out of 1. Because remember that the area under the curve always adds up to 1. So if we chose this confidence interval here, that means that we are 1.96 standard errors away from the true statistic on both sides. That 1.96 is unfortunately just something you have to remember. You can look up other numbers for other percent confidences. To find the interval through the normal curve, you'll find the sample statistic. And we use means for doing normal curve stuff because the central limit theorem, the sampling mean is normally distributed. So our sample statistic is the mean of some sample. So I'm going to run back to my RStudio and show you what that looks like. So this is what question 14, question 15 would be about. I'm just going to start a new file just to show you what it looks like. So to find the upper and lower bounds, you must first find the standard error. The standard error is SD, or standard deviation, divided by square root n. I'm not going to load all the libraries and all that because I want to show you what it could look like. Let's say we're using Pew still from our notes. So Pew, I'm going to drop all the NAs just to make sure there's nothing in there that could mess me up. And then I want to summarize SD equals the standard deviation of some variable. So this is going to make me a new little printout where they calculate the standard deviation of this numerical variable. Now, I'm going to save this and call it SD. I'm going to move on to the next thing. So mean, or I'll call it stat for consistency. So stat Pew again, dropping my NAs, and summarize, and you guys know how to do this. Stat equals mean of the numerical variable. Okay, and finally we're gonna do n actually first. Now n is a little interesting because it's still a summarize function, but it looks a little funky. We're gonna drop NA again, pipe summarize, and then we're going to say n, the name of our thing, equals n in parentheses. The n with the parentheses is a function for counting. So we're assigning counting all the observations to this thing called n. And then finally, the SE, Pew, drop NA, summarize, and then SE equals ST square. Now, if you ran this, you would come up with an error. And that's because whenever you do this, where you're adjusting the data frame, dropping NA, summarizing, it's going to make a data frame. And because it's in a data frame, when you try to use it in this equation for the standard error, you won't be able to get a number. And that's why we have to pull the number from each of these data frames. And we'll pull it here too. So what we'll get out of this is that we can put all of our different parts of our equation into the confidence interval, and we'll do a vector for this. I'll call this vector CI for confidence interval vector, for instance. And to make a vector, we're going to use C. So C is like how we assign things to a string. We want to write the upper and lower bounds. So we're going to start with the lower bound because that's how it's going to print out. So it's going to be the stat minus the 1.96 times the standard error. Okay, so that's our lower bound. So we have stat, which is our anchor, is our center point, and we're going 1.96 standard error away. And that's like our half of the 95% confident interval. To do the upper bound, we don't need to make a new string. We can just say comma stat plus 1.96 times SE. So we got our lower bound and our upper bound. If you were to put this on a normal curve, we could see that stat is our center and the 95% confidence is going out from the left and the right. The outcome of this code is simply the interval boundaries, and we read it just like how we read get CI. You can do all this normal curve stuff in R, just like how I showed you here, but you can do it by hand too, because it's purely mathematical. Just follow the equations for finding mean, standard deviation, standard error, and count the number of observations for n and plug them into these interval bound equations. One thing to note, for the normal curve method, the normal curve is just an approximation of the sampling distribution. We have to make an assumption that the sampling distribution is a normal curve or normal distribution. In reality, it isn't. It's just a distribution that looks very close to the normal distribution. For this reason, the bootstrapping that we did back here would be typically more accurate of the larger samples, but the difference between the two for larger and larger samples eventually vanishes. All right, I hope this video helped you understand confident intervals a little more. If you have more questions, please let me know and post them in the comments below.